Today I want to show you how to use the Baselabs Create visualization as a tool to diagnose a data fusion system. For this purpose, I've used Baselabs Create to configure a 2-sensor radar and camera data fusion. Each sensor has a measurement model, detection model, and a track proposer. And as one can see, there are a fair number of parameters. It is important to correctly set the parameters to avoid irregularities in the tracker. Therefore, before starting, let me highlight two categories of parameters which cause common errors. In the first category, we find the physical mounting position. Sensors are normally mounted on the outside of the car, but the Ego vehicle's coordinate system is centered on the center of the rear axle. Thus, sensor positions must take this offset into account. The second category involves the sensor's statistical characteristics, for example, sensor noise and detection probability. Sensor noise is set, for example, in the measurement model and in the track proposer. Here you will need to get the sensor manufacturer's specification or use your own results from experiments. Another sensor characteristic is the detection probability, and it is set in the detection model. If this value is too high, the system might be overly sensitive to misdetections and easily discard tracked objects. If the detection probability is too low, the system might report false positives. After that introduction, I will start our data fusion system. Our application consists of a video showing the Ego vehicle view with bounding boxes highlighting the tracked objects, and a bird's eye view showing the field of view of each sensor. The field of view shows measurements as open circles and in the color of the sensor. Tracks are shown as solid diamonds. The heading and speed are shown as a green arrow. Covariance is shown as a green ellipse. The associated measurements are connected with lines to the track, and the predicted measurements are also shown connected with lines to the track. Now notice the vehicle overtaking from the left. If I zoom into the field of view, we see the camera measurement, which is then almost immediately tracked. Seconds later, the vehicle also enters the radar's field of view, and we see an unassociated radar measurement appearing. The radar measurement suspiciously lags the track by about 3.5 meters. That's the distance from the front bumper to the rear axle. So we can see here's the track and a field of view, and we can see the bounding box. We can see the camera measurement is associated with that track, but this radar measurement is not associated with the track. And now you'll notice that if we let the video run a little bit more, that radar measurement is turned into its own track. Now all of a sudden we have two tracks. We have the track from the camera measurement, and we have a new track which is associated with that radar measurement. And we can see it's behind that camera track. So here we have the covariance for the track that's generated from the camera measurement, and this is the covariance for the track that's generated from the radar measurement. And notice that this covariance is suspiciously small. Does the radar sensor really have such good noise characteristics? In summary, the system does not realize that the camera measurement and the radar measurement are from the same object. And as mentioned earlier, likely causes include too low sensor noise and an incorrect mounting position. So going back to Baselabs Create Data Fusion Designer, we can see our suspicions confirmed. The mounting position is incorrectly set at 0 meters along the x-axis. In reality, the sensor is located 3.5 meters from the center rear axle. Also, the radar's range noise is too low. It should be set to 1.2 meters. So let me correct these values. I change the settings and then I'll regenerate the data fusion. When I rerun the data fusion application, I now see that both camera and radar measurements are associated with the track, and the object is identified by a single track. Thank you for watching.